right, now we're going to talk about half-life. And first of all, defining exactly what that means. Half-life is the time required for half of the radioactive isotope to decay into the daughter element. So it's a time amount, and they vary depending on the radioactive isotope. Like carbon-14's half-life is 5,738 years or something like that, which seems like a huge amount of time, although others have millions of years for their half-lives. And then there are simple ones that have, their half-lives are like 20 seconds. So the time intervals do vary based off of which radioactive isotope we're talking about. Okay, and you're going to have to be able to read these graphs. They're exponential decay curves. You probably have seen them in math before. But as you can see, it does this like curve downward fashion. This example is plotting the half-life of strontium-90. And strontium-90's half-life is 29 years. So basically, if we start out with a 10-gram sample here, and we go one half-life, which is down here, that interval is 29 years. Okay? And in that process, half of the sample is now no longer the radioactive isotope. It is now the daughter element, the stable one. So only half, 5 grams of the original sample is left. If we undergo another half-life, which would be this interval, is also another 29 years. And in that process, another half of the radioactive isotope is going to change into the daughter or the new element. And what's left over after that time has elapsed, the second half-life, you would have 2.50 grams. So at this point of the graph, the total elapsed time is 58 years. So 2 half-lives have passed in 58 years. As you can see, the process is very simple. You're basically just dividing by 2 in order to get the new daughter element, and or the original amounts, what is left over, you divide by 2. And if you don't like dividing by 2 and you think like fractions, you're also welcome to think about it as multiplying by 1/2. So some people like to use the multiplying by 1/2, some people like to use the divide by 2. I really don't care which one you choose to use. I typically just divide by 2. So be able to read the decay curve. There are some on the lab, and we're going to graph our own from our data in the lab that we're going to gather today for Yahtzee. And you'll be able to tell, you can look at the graph and say, okay, if I start up here and I have 10 grams, where on my graph do I have 5 grams? Oh, I have 5 grams right here, okay? I look down here, how much time has passed? I know the half-life of the particular element. Okay, so you just can read the graph, divide it by 2. That's going to be the half-life amount off of the x-axis. Okay? Now, there are 2 ways to work these problems. We give you the formula on the sheet here. Amount remaining, I like to say, is like the final mass. Initial amount would be like your starting mass. And then it's 1/2 raised to the n, where n equals the number of half-lives. Now this formula is very simple and easy to use if you know the number of half-lives. If you don't know the number of half-lives, because you're missing either the half-life time or the elapsed time or total time, then it becomes a little bit more complicated in math, and you have to do natural log and a bunch of different math steps in order to solve for the exponent. You're welcome to do that, but in those particular cases, it will probably take you longer to do all of that substitution in math with the natural logs than it would be just to use the chart method. So if you know the number of half-lives, you can plug it into the formula and get the answer very easily. If you don't know the number of half-lives, I would stick to the chart method. Okay? Now, a couple of things are identified here too. They use a little t to denote the elapsed time. This is also what I call total time. And the big T is the duration of the half-life, which I call the half-life time. Okay? And I'm going to be referring to them as we go along throughout these example problems so you know how to work these. As you can see, the table method, you can set it up with these kind of columns or you can do rows. I like to do rows, so you'll see my system in a minute. But the number of half-lives is listed. You can put the elapsed time. You don't necessarily need to have that particular one in the table, but then you need to have the amounts as you're going along. And like I said, here you're seeing this one do the 1/2, multiply by 1/2. So 1 half-life has passed, which is 29 years. The 10 grams gets multiplied by 1/2. I say divide by 2. We end up with our 5 grams. 2 half-lives have passed, which is a total of 58 years. Now we have to multiply the 10 grams by 1/2 times 1/2 to get this. Or you could divide the 10 grams by 2 and then divide it again by 2, whichever way you like to approach it. As you can see, the table method can continue on, so you would know how many grams at any particular half-life. If you just keep listing it out, that will give you those values. So let me show you some examples of the way they're worded and what type of variables you'll have to solve for, because there's a bunch of different ways they could ask these questions. So for instance, the half-life of thorium-227 is 18.72 days. How many days are required for 75% of a given amount to decay? When they give you stuff like this, they don't give us a starting mass, they don't give us an ending mass. All they tell us is the percentage that went away and the half-life time. So what I do in situations like this, and this happens a lot in AP as well, where they don't give you real numbers to work with, you have to just make your own up. So guess what numbers I'm going to make up? I'm going to use 100 grams as my starting amount. Okay, this is going to be my starting amount. And I'm going to go to, what is 75% of 100? 25, very good. So this is going to be my end mass. Now, to set up the table, like I said, you can do columns or rows, whichever you feel more comfortable with. I like to do rows. So I'm going to start with 100, and this is at 0 half-lives. So after 1 half-life, how much of my sample should I have? Because I'm going to do what? Divide by 2. So I should have 50, right? After 2 half-lives, I once again divide by 2. And then I'm going to have how much? 25 grams. Now, is that my ending amount? Yes, so I get to stop. But now I know how many half-lives have passed. I have 2 half-lives that have passed. And if each half-life is worth 18.72, can't I figure out the total elapsed time? What could you do here? You would multiply them by 2. So 18.72 times 2 gives us what as our total elapsed time here? Yes, days, thank you. Don't forget your unit. And when you're doing significant figures with this, pay attention. The only real measured value here is this one. So since it has 4 digits, I'm going to use 4 digits in my answer. Okay, so you might see something like this where they give you a percentage and some of the times. You have to kind of invent your own numbers here. Now looking at this one, different presentation, different information in the problem. So let's identify what they gave us. We have iron 59, and its half-life is 44.5 days. How much of a 2-gram sample will remain after 133.5 days? So what did they give me here? Lots of information. They gave me 2 grams, which happens to be the starting amount, right? Okay, so I can just kind of build my table here. What else did they tell me, though?
the last year's from the farming.
They told me what? Besides the 2 grams? What did they tell me?
The half-life.
Half lifetime and the
Days that they're looking for.
the total or the elapsed time of the whole thing. Yes, the total time. What can I figure out from knowing the total time and the half-life time?
Divide.
I can divide and figure out the number of half-lives. So yes, so you're going to take your total elapsed time divided by the half-life, which is 133.5 divided by 44.5. How many half-lives have passed? 3. So now I know how long to build my chart, right? I know how long to go out my chart. So 0, 1, 2, 3. I know that I need to extend my chart out to 3 half-lives. Then all I have to do is start dividing by 2. So if I divide by 2 or multiply by 1/2, remember you can do that, multiply by 1/2 if you like, I'm going to end up with 1 here. I go ahead and do it again, divide by 2, multiply by 1/2, either way is fine. I'm going to end up with 0.500. I'm going to stick with 3 sig figs because that was my original mass number. And last but not least, divide by 2 one more time. Multiply by 1/2 or multiply by 1/2, and I end up with 0.250 grams. This is my amount that would remain after 3 half-lives, and that would be your final answer. So that's one way they can present it for you. They can give you the original amount or the starting mass, both the half-life time and the total time, and you have to find the ending mass, or what will remain after the number of half-lives. In this case, it was 3. So let's look at the next one. Let's pay attention here. Gallium has a half-life of 68.3 minutes. How much of a 16 milligram sample will be left after 2 half-lives? Any ideas about the most efficient way to work this one? We know 2 half-lives, so we could use the formula. Since we know the number of half-lives, it's very simple. We can use the formula. Okay? Remember, it's like the final mass equals the starting mass. 1/2 raised to the nth power. If we know n, which we do, we can easily use that formula. So we could put in here the 16 milligrams, multiply it by 1/2 raised to the 2nd power. And what's that going to give us in our calculator? It should give us 4. Now that's one way to do it. 4.00 we would go with for the sig figs. Milligrams is our unit. If that doesn't work for you, you could just easily set up the chart. Start at 0, 1, 2. Put in your 16 here. Divide by 2, get 8. Divide by 2 and get 4. Okay? Either way works. But you could consider the formula in this case because they tell you the number of half-lives. You don't have to worry about doing any kind of natural logs in there. Okay? So that was a simple one. You just had to recognize that they gave you lots of information. That 68.3 was also extra information that you did not need. That's called a distractor, by the way. So don't let them distract you. Okay? Now let's take a look at this one. Let's figure out what's being presented to us and what do we go from here. This one's very interesting. We know the what? Half-lifetime, because it's 7.04 years, uranium-235. So this is T. What else do we know? What's the other thing we know here? So the time elapsed, this is little t, or the total time, yes. What else do we know?
Sample remaining.
Sample remaining, the ending amount. This is the end. Mass, the ending mass. So, what are we trying to find here?
The initial sample.
We need to find the original or the beginning amount, starting amount. So in this case, we're going to need to work backwards. So you could easily figure out the number of half-lives. How do we do that? T divided by T, little t over big T. So we have 28.2 over the 7.04. What is our number there? What's our number of half-lives? 4. We're going with the whole number of 4 there, yes. So then we know how to set up our table, but we have the ending mass, not the original beginning starting amount. So we're going to have to work backwards. So I'm going to start here. We have 4 half-lives. I'm going to make my chart go backwards. And if I have 12.5 grams to start, what do I need to do to work backwards to my original amount? I'm going to multiply by 2 instead of dividing by 2. Exactly. So let's multiply by 2 along the way. So 12.5 times 2 gives us 25. 25 times 2 gives us 50. 50 times 2 gives us 100. And last but not least, 200. Don't forget your dot to make it have 3 significant figures. And your unit, this would be the final answer. Now, you could also use the formula because you do know the number of half-lives. The only thing is you would have to put the 12.5 over here. You would have to put like x in here, and you would have to do 1/2 raised to the 4th power, and then you'd have to do some algebra backwards. Okay, to get it all over to the other side. You still would come out with 200 though. Okay, either way is fine with me. All right, what is the half-life of a 100-gram sample of nitrogen-16 that decays to 12.5 in 21.6 seconds? So we know the starting, we know the ending, and we know what else? The time elapsed, the total time. Very good. We're missing the half-life. We don't know the half-life. So we start by just setting up a table here. We're starting at 100. Let me rewrite that. That looks like 1,000. All right, 100. At 0 half-lives, at 1 half-life we have 50. At 2 half-lives we have 25. At 3 half-lives we have 12.5. So the number of half-lives is 3. Now what can I do with that information to figure out the half-life time? T divided by T equals 3 here, right? So we have 21.6 over T equals 3. Really that means 21.6 divided by 3. So our half-life is going to be what? About 7, but let's get the exact number, use our calculator. 7.2 seconds, very good. So this time they wanted you to figure out the half-life time. There is one last little added problem that you might see, and it's probably the easiest of them all if you just think about it for a second. When you have to find a factor, or they could use the word fraction. So when they say factor or fraction, They just want like a coefficient number to work with. So, in this particular case, we're not given any masses. We're only given the total time, the total elapsed time of 51 minutes, and the half-life of 5.1 minutes. What can I determine from that information? Yes, we're going to do that, but what can I determine from the 51 and the 5.1? It's going to have 10 half-lives because I go ahead and take my 51 divided by the 5.10. That means I have 10 half-lives. Now, as stated back there, the only thing you have to do here is once you figure out the number of half-lives, to find the factor or coefficient you're going to multiply by, take that 1/2 and raise it to the 10th power. And then you can leave it in its fraction form. So this would be 1 over basically 2 to the 10th power. If you put that into your calculator, it ends up being 1024, which is a very small number. Okay? So find the number of half-lives and then just do 1/2 to that power, and that will give you your factor or your fraction that you need. Okay? So these are the types of problems that you will see the way they're worded. Sometimes they ask for the starting mass, sometimes they ask for the ending mass, sometimes they ask for the half-life time, sometimes they ask for the total elapsed time. Really just depends on the way it's phrased. You have to pay attention to those.